So, hello friends. So today we will study another numerical based on the energy method to find natural frequency. So a system is shown here. You can say a mass is suspended by a spring horizontally, and the stiffness of the spring is given, and we have to determine this natural frequency of the system. The thing you should be careful is the spring is attached not to the circumference. It is attached at a point eccentric from the circumference and from the center line. So it is given as R, and it is given a distance 35 from the center line of the disk, and also it is at a radius R, and also mass is suspended from the circumference of the pulley from the other side. So to find the natural frequency, let's draw this figure again. So if you call this point as A, when this mass moves a distance x in the downward direction, at a displacement x, then this pulley will also rotate in that direction like this, and this A will be moved towards A1. Let's call that point A1, and that also will be x, same distance. And also accordingly, the spring will be elongated in the circumferential direction, and if I call it as B, then that will be elongated to B1, or that will move to B1. Let this be an angle theta. So taking the radius and arc length equations, we can write A1 is equal to R times theta, because R is the radius of the pulley, and if that is not equated to x. Similarly, B1 can be written as, since R distance is here given here, that will be same as this radius, because that is a vertical from the horizontal line of the spring towards the center line of the pulley. So this R will be the radius here, this also will be R. So this arc length cut by B dash will be equal to small r into theta. That will be equal to x1. I am calling it as x1. So if you know this analogy, then equation becomes easier. So applying energy method, and energy method we know total energy remains constant, law of conservation of energy. So total energy, let's take which are the total energies associated with this system. First one will be kinetic energy of translation of this mass m, and that will be half of m times x dot square. X dot is the velocity, that is x is the displacement, x dot is the first derivative of displacement, that is velocity. And second one will be kinetic energy of rotation associated with the disk, and the displacement here is also x, but since it is rotation motion, instead of m we will take moment of inertia I, and instead of x dot we will take theta dot x square, and we can reduce it here itself. We know m moment of inertia is equal to m r square by 2, and theta is given, so we can reduce it as 1 by 4 m r square theta dot square. And the third energy associated with this is potential energy of spring, and the equation is half of kx square, but here the spring is moving at a distance x1. We have called that one x1 because it is not equal to x, because spring is connected at eccentric point. So half kx1 square. So these are the three energies associated with the system, and if you can find these three energies, the answer becomes, if you have to find the natural frequency, you just equate these three energies to the constant, or you take the derivatives and equate it to 0. And before that, we should substitute. We have x we already have an x is equal to r theta. So it is necessary because we have an x dot here. So to find x dot, so x dot will be equal to how much? X dot will be equal to r theta dot. Similarly, we have x2, sorry, x1 that is equal to r theta. So if you can substitute this in this equation and apply total energy conservation, so half of small letter m and x is equal to r half mx dot square. So it will be half r square theta dot square plus we already have the rotational energy equation, that is 1 by 4 mr square theta dot square. So we can keep it as 1 by 4 m r square theta dot square plus kinetic energy of the string half k, and instead of that x1 you can substitute r square theta square. This will be equal to a constant, or you can equate that towards a 0 by taking the differential with respect to time. So d by dt of this equation half m r square theta dot square plus 1 by 4 m r square theta dot square plus half k r square theta square will be equal to 0 because differential of 0 will be 0. So the taking this differential, so half m and r square remains constant, and theta dot square can be differentiated as 2 times theta dot times theta double dot of the second derivative, and 1 by 4 m r square remains constant, and again there is a theta dot square here, so that theta dot square can be differentiated as again 2 theta dot theta double dot plus again half k small r square, and theta square can be differentiated to theta dot is equal to 0. So in this 2 and 4 will get cancelled into 2. So that will be 2, and also theta dot is common, so you can equate theta dot to 0. So 2, this 2 get cancelled, so and theta dot get cancelled everywhere, and you will be left with an equation half of m r square, and to this 2 and this 2 also get cancelled, sorry. So you will be left with an equation m r square theta double dot plus 1 by 2 capital M r square theta double dot plus k, this 2 also get cancelled, k r square theta equal to 0. And if you can make it this theta double dot as common, so theta double dot is equal to m r square plus half m r square plus k r square theta is equal to 0. So making it into the equation of simple harmonic motion, so theta double dot plus k r square divided by m r square plus half m r square, that is dividing by this term to the entire equation, theta is equal to 0. And we know the equation of SHM as simple harmonic motion as theta double dot plus omega n theta is equal to 0. So comparing this equation with the simple harmonic motion equation, we will get 1 and 2 implies omega n is equal to kr square divided by, okay, this is small m, sorry, I accidentally got capital M. Yeah, that will be mr square plus half capital M r square, and consequently frequency or natural frequency will be 1 by 2 pi omega, so that will be 1 by 2 pi omega square n, sorry, omega square n. That is equation of simple harmonic motion, and omega square n will be kr square by mr square plus half mr square, and omega, we know frequency is 1 by 2 pi omega, so 1 by 2 pi into root of kr square divided by mr square plus half m r square. So this will be the equation of natural frequency of the system, and there is value given for small r as 35 mm, capital R as 50 mm, and mass as 10 kilogram, and small mass as 1 kilogram. So this will be our small m, capital M is given, and this will be our k. So everything else is given. So if you can substitute that in this equation by taking the units, you will get frequency is equal to 1.438 hertz. That will be your answer. Substitute k, r, m, r into this equation and you will get the frequency as 1.438 hertz. So that will conclude the answer. So this is how you solve a numerical which is given by this figure. So if you can understand this method, whatever be the position of the spring, you can determine the equation for natural frequency and substitute the values. Here the spring was attached at this position. If spring is attached in below, same thing you should do. And also if spring is attached at circumference, you already know. So then this x and x1 will become same. So similarly apply your mind and do the problems according to the position of the spring. Thank you.